Welcome to The Explainer. Today, we're diving straight into the exact methodology engineers use to defend modern connected vehicles against digital heists. As our cars essentially become giant smartphones on wheels, the security shield protecting them needs to be absolutely airtight. That shield is called TARA. Here's our agenda for today. Section 1. Why cars get hacked. Section 2. The TARA methodology explained. Section 3. Identifying targets and assets. Section 4. Mapping the attack path. Section 5. Scoring the cyber risk. And finally, Section 6. Treating risk and future-proofing. Let's get right into it. Section 1. Why cars get hacked. You might remember the infamous OwnStar attack reported by ZDNet. It's a terrifyingly perfect example. Attackers used a really cheap hardware device to intercept mobile data, effectively turning a standard mobile app into a master key. They could remotely track and unlock General Motors vehicles without the owner ever knowing a thing. It's a classic driver-to-machine attack, where everyday tech is exploited to force unintended behavior. Because of nightmare scenarios like that, international regulators absolutely had to step in. We now have strict standards like ISO/SAE 21434 and UN regulations 155 and 156. These aren't just polite suggestions. They mandate a standardized threat analysis for every single new vehicle type. If an automaker wants to sell a car today, they have to maintain a structured cybersecurity management system for the vehicle's entire life cycle. Section 2, the TARA methodology explained. So, what is TARA? It stands for Threat Analysis and Risk Assessment. Found in Clause 15 of the ISO 21434 standard, it gives engineers a really powerful structured roadmap. It's a systematic 7-step process. You start with asset ID, then define threat scenarios, determine your impact rating, map out the attack path, calculate the feasibility rating, produce a final risk value, and wrap up with risk treatment. But wait, before we can even execute those steps, we have to define our scope. We do this by defining what we call the item. Basically, we're drawing a strict boundary around a specific system that performs a vehicle function, and that includes its sensors, the controllers processing the inputs, and the actuators making things happen physically. Now, obviously, not every single bolt and wire needs this intense level of scrutiny. We do a quick cybersecurity relevance check by asking 4 critical questions. Is it an electrical or electronic component? Does it contribute to safe operation? Does it collect or process user data? And does it connect to networks? If you answer yes to any of these, that item is cybersecurity relevant and a full TARA is required. Section 3. Identifying targets and assets. Okay, step 1 of the TARA framework, cataloging our assets. An asset is simply anything of value. That could be executable code sitting on a drive, configuration data, or communication packets flying across the vehicle's internal network. You literally cannot protect something if you don't even know it's there. To figure out why a specific asset matters, we use the expanded CIA+ model. We ask ourselves, could an attacker compromise confidentiality, like leaking a driver's private location data? Could they attack integrity by altering a braking command, or hit availability by crashing a critical ECU? In Automotive, we also look heavily at authenticity, authorization, and accountability to make sure every action is verified. Let's anchor this with a concrete case study that industry pros use all the time, a power window system. Our item boundaries are the buttons, the door controllers, and the window actuators. The prime asset, the CAN messages. Those are the command signals on the car's network. And the property we're defending is integrity. If a hacker can inject or alter the window close command, they could bypass the anti-pinch safety feature, which is a massive physical risk. Section 4. Mapping the attack path. Next, we literally have to think like a hacker. We map out the attack path step by step to see how they'd reach our asset. We trace the digital route from an external entry point, say Bluetooth or a cellular modem, through an intermediate pivot point, like a gateway ECU, right down to the target asset, like that window CAN message. We're mapping out their entire master plan. Section 5. Scoring the cyber risk. Once we have the hacker's path, we score the potential impact from negligible all the way up to severe across 4 categories: safety, financial, operational, and privacy. Whichever one of these 4 categories scores the highest, well, that simply becomes our overall impact rating for that specific threat. Then, we estimate the attack feasibility. Basically, how terrifyingly easy or incredibly difficult is this hack to pull off in the real world? We figure this out by looking at the time required, the level of specialist expertise needed, the hacker's window of opportunity, and the equipment necessary. That gives us a feasibility level from very low to high. Now we put it all together in the risk matrix. We brilliantly cross-reference our impact on one axis against our feasibility on the other, and it spits out a definitive risk level from 1 to 6. A level 1 might be fine as is, but a level 5 or 6, that tells us we need immediate, serious cybersecurity controls.
Section 6. Treating risk and future-proofing.
For those high-risk scenarios, we write a rock-solid cybersecurity goal. It has to dictate exactly what needs to be achieved without forcing exactly how to do it. Going back to our power window, a great goal is the integrity of window control commands on the CAN bus shall be protected against unauthorized modification. It's clear, it's direct, and it gives the engineers a strict mandate. Based on Clause 15.9, engineers then make a calculated decision with 4 options. They can avoid the risk entirely by ripping out the vulnerable feature. They can reduce the risk with security controls. They can share the risk via a supplier contract, or they can consciously decide to retain the risk as long as it's properly documented. Now imagine doing this complex math for every single tiny component in a car. You literally can't do it manually. Spreadsheets break down incredibly fast when you have hundreds of assets, and they totally lack traceability. That's exactly why the industry is rushing toward automated, highly specialized Tara modeling tools that offer scalable, model-based integration. Here is the biggest takeaway from our explainer today. Tara is not a one-and-done checklist that you file away. It is a living, breathing shield. As our vehicles evolve with 5G networks, vehicle-to-everything comms, and massive over-the-air updates that literally change the architecture on the fly, your Tara has to be continuously updated right alongside it. Which leaves us with a pretty wild question to end on. As our highways turn into hyper-connected digital networks and cars talk to smart cities in real time, what entirely new, terrifying vulnerabilities will the next iteration of Tara have to expose and defend against? The methodology is definitely here to stay, but the threats are always evolving. Thanks for joining me on this deep dive, and keep your systems secure.